Well, welcome everyone to this February session, technical session of DigiShape. And today we have Fanny Rebiffé from Marin, and she's going to answer a question today that is, how can a computer sail an optimist using reinforcement learning? So, Fanny, I give you the floor. Let us know.
Thank you. Do you hear me well? Yeah. So this presentation is part of a bigger program that is an end-on experience. We won't go through all this program, that takes one day at least. So today I'm going to focus on the context of this project and the results we obtained. But first, let me introduce myself. My name is Fanny Rebiffé. I am a data scientist here at MARIN, which is a maritime institute. And I have also studied physics through my mechanical engineering background. But even with this physical background and my maritime work, I have to say, I don't know how to sail. Whereas kids, they can sail even without knowing the details of aerodynamic or hydrodynamic. This was recorded in our basin in last year to check the feasibility of our program, AI Sail, if it was possible or not to sail in our basin. Why kids can learn without those physical details? Because knowledge is not only about can be read in book or written as equation. Knowledge is also about being able to feel or to take instinctive decision. Knowledge is also implicit. But implicit knowledge is not always easy to share, as you can see on this drawing. And it's also not always easy to explain or to acquire it. So how we can gain this implicit knowledge like kids do by trial and error process. And this process is called reinforcement learning in education and in machine learning. Reinforcement learning is a machine learning algorithm that is part of a bigger field, which is the artificial intelligence, together with robotics and other fields. Machine learning is maybe a bit more famous for supervised learning and unsupervised learning. The first one is used for prediction and the other one for data exploration. But today we are going to focus on reinforcement learning, which is an algorithm that learns to optimize the decision process through interaction with a dynamic environment. We can use it to optimize combination or decision process. So today we are going to focus on the automation part. It has proven to be successful in other fields than the maritime one. So here an example with games, with AlphaGo or robotics. With AI Sail, we aim to explore the possibilities and limitation of AI. It's not a commercial project. So in the context of reinforcement learning, the AI is called an agent, and in AI Sail, the environment is the optimist in the basin. They are going to interact through action from the agent and observation or state from the environment. And that would be it if we were using a classical controller or traditional program. We would say to this program how to react given a certain state. But here we won't tell our agent. It has to figure it out by itself. But we still want to tell him what is a good action and what is bad action, or at least what is a sequence of good action. So for this, we are going to give it feedbacks that we call rewards. Our target is to reach that our reinforcement learning agent reach the opposite side of the basin by sailing upwind. We have some constraint. Oh, sorry. Yeah. So we have equipped our Optimist with sensors that will be the eyes of our agent and actuators that will be the arms of our agent. We have some constraints. We don't want the boat to crash into the walls. And we can also put our goal. Here I put treasure to signify the goal we have. And when reaching one of those conditions, so either having reaching the walls or reaching the targets, the agent will put an end to the sailing attempt. So the environment and the agent are going to interact. And at each step, we can also give intermediate rewards to guide a bit the agent towards the final reward. This final reward will be collected by the end of the episode when the agents reach an end condition. It can be a positive reward if it's the target that is achieved, or a negative reward if it's the walls, for example, that are eaten. A loop of this interaction is called a step, and a sequence of those steps is called an episode. It ends with a final condition or an end condition, and then the agent gets the final reward. The goal of our agent is not really to sail upwind. It doesn't really care about it. What it cares about is collecting as much reward as possible. And this cumulative reward, we call it the return. Now let's have a look of how the brain of our agent is composed. It's composed of a memory that we called a replay buffer, in which it will store its experience. It has also neural networks that it's used to take actions, but also to analyze them. And finally, it's used randomness, either at start, when it doesn't know how to sail, or even after a certain time, even if it knows how to sail, it will still use some time to time randomness to explore new strategies. In reality, our agent is not directly connected to the basin. It is connected to our simulation code that will act like a digital twin of the real Optimist. It has several advantages, among which, when disconnected from the basin, we can train our agent faster, safer, and it also makes the development more easier. There are a lot of reinforcement learning projects, but among them, few are applied to real case, and some are applied to real case, but still with some constraints that make the problem easier. It can be discrete action or deterministic environment. There are few cases that are applied to continuous action in a stochastic environment, which is the case AI Sail. And most of the time, those projects will suffer from degradation of the strategy of the agent that has been learned in the simulation when it's applied to reality. So we were also facing this challenge for AI Sail. And of course, your simulation is made of simplification. And it can be that your agent will find them and use them to achieve the goal in an undesirable way. So here, this agent, it will work well in the simulation, but probably not in reality. Thus, the fact that here at Marin, we have both simulation and basin is trained for reinforcement learning and AI development. But this was only doable thanks to many colleagues. Today I'm the one who talk, but behind me there are a lot of colleagues working on this project. And together we have been through a long path that took a year to first buy the boat, create the simulation, connect the boat and the simulation, train the agents, and finally give the demonstration in November of the AI sailing the boat in our basin. Now let's go back to the schema to see what data scientists face as a challenge when training an agent. So if we go back to the example of kids learning how to sail, different kids will have different way to learn, and it's the same with reinforcement learning. There are different agents and they will have different way to learn. So first we have to choose an agent, but same as kids, for example, a kid that would not have sleep well before sailing may be able to focus a bit less longer. So your agent can also focus a bit less longer. It can be a good thing or a bad thing depending on your application. And this is tuned with what we call hyperparameters. That it's also something we have to choose in advance. So one of the challenges is to pick the right agent for the problem we have and the right hyperparameters. Another challenge is to design the rewards correctly and to select the proper end conditions. In movies, when things go wrong with AI, it's because AI is trying to kill us. Whereas in reality, when things go wrong with AI, it's because AI does what we ask it to do, but not what we want it to do. Let me give you an example. Here we have designed a very tiny final reward and big intermediate reward. So maximizing the cumulative reward means looping and collect as many intermediate rewards as possible instead of reaching the target that would put an end to the episode. But if we don't give any intermediate reward at all, then our agent may be lost and never find the target. Another challenge we face is to design properly the state. Like kids, if you give too much information, they may be overwhelmed and not being able to correctly decide. But if you don't give enough information, if you blind them or do not let them feel the motion of the boat, they may also not be able to sail properly. So here again, we need to find a proper balance between too much information and not enough. Finally, the way or the environment you train your agent in also has huge impact on the behavior of your agent. If you want your agent to be able to adapt to new conditions, you can randomize, for example, the wind conditions or the initial position and things like this. But of course, if you make the training too complex, it may take way too long for your agent to learn what is a good behavior. And finally, one of the challenge itself is to find a proper combination of all of those. It can be that your reward is well defined, but just the agent you picked is not able to handle this reward, but another one could have been great with it. So I presented the main idea of what is reinforcement learning and the advantages of it, but it has also some drawbacks. Those drawbacks can be addressed with other variants of reinforcement learning. We can see reinforcement learning as a Lego on which you can plug other Lego blocks to do more complex tasks. So one example is offline learning, model-based, hybrid control, physics-informed, curriculum learning. There is another variant that is not called reinforcement learning anymore, but is also quite close, that is called evolutionary strategy. At Marin, we are studying those variants as well, but it's not what we used for AI Sail. Now let's have a look to the results and our setting for this experiment. So as a reminder, our target is reaching the opposite side of the basin while sailing upwind. For safety reason, we also have some constraints like not hitting the walls. And we also pay attention to the behavior of our agent before putting in the basin. We didn't want it to jibe, which is turning with the wind in the back. We also wanted to respect the sailing rules. So avoiding schooling. Schooling is moving the rudder so fast that it actually propels the boat without any need of the sail anymore, like a fishtail in the end. So we didn't want to see this behavior. We didn't want to see rocking neither. So rocking is moving the ballast from one side to another. And what we have named cheating, which is moving the sail fast as well, and the way of cheating that we didn't want to see. We train our agent without wave, but with randomized wind condition and starting position. The actions our agent has to deal with is the rudder angle, the ballast position, and the line length. The reward we have designed here is a continuous reward for how far the agent managed to go from one step to another. And the final reward are a big penalty for hitting the walls, a bonus for reaching the target, a penalty, and of course, for all those last reward, it was with an end condition as well. So an end condition and a penalty for too high roll motion, and a bonus if the agent managed to survive more than 6 minutes without hitting the walls or having a high roll motion. So those are final reward. And the combination of the two were the return that our agent was trying to optimize. What our agent could see was its position in the basin, its yaw, its forward speed and acceleration, its roll, its wind speed and heading. And finally, the agent we have chosen here in this example, but we have trained many, is TQC. I won't go into details, but we can go back to it later in the question. And to give you an example of one of the hyperparameters we had to tune. So for the kids, the example I gave was how far or how it is able to focus. Here, we can, with a parameter that is called the discount factor, we can decide how far our agent will see in the future, or how far it will be interested by a future reward. And if this discount factor is small, we say that our agent is myopic. So that's one of the hyperparameters we have chosen here. Now let's see how the training went. So at the beginning, the agent is acting randomly. So sometimes it hit the walls, sometimes it's run out of time. It barely reached the target at the beginning, but after 30 minutes, it already reaches the target often enough to know where it is and what's the goal and how to optimize the rewards. Then it's a matter of fine-tuning its strategy. So after 1 hour and a half, the strategy is already quite consistent in reaching the target. If we look at the other behavior we were paying attention to, which were jibe, shitting, schooling, and rocking, we see that at the beginning it used it a bit more to reach the target, but then it starts to decrease those behavior because they are not the best behavior to reach the target. They are not the fastest behavior. We didn't have to give a penalty for those because the agent was reducing them by itself because it's not the fastest way. So at the beginning of the training, as I say, the agent is doing random things. Here it is schooling, there it's jibing, also acting randomly. But after already half an hour, it starts to survive and sail kind of okayish. After 1 hour, it does proper tack. It is just still a bit slow. And finally, by the end of the training, after 3 hours of training, the agent is able to sail properly and doing fast tacks to reach the target. The one on top here is jibing. So it's not a good way to sail, but at least it's not reaching the walls anymore. And the one at the bottom is already at the target. So it's way faster than the others. Now, this is the setup inside the Optimist. You can see the actuators. So the line length, the ballast position, and by the end of at the back of the boat, you can guess the actuators that moves the rudder. This was the demonstration we gave in November. So we trained our agent in the simulation, and then without further training, we gave it the real Optimist to sail, and it managed properly to step into reality and sail accurately. During the demonstration, the fans were set low in order to be able to speak and hear each other. So also the sailing is a bit slow. We also trained the agent with different wind speeds to be able to adapt to new speed. And here it reached the target. So in conclusion, what we achieved here is to bridge the gap, or at least to participate to bridge the gap between the academic methods and the maritime applications. We are not there yet to sail in the ocean, but sailing a real Optimist is already a step towards real application. And also we managed to go with our agent from the simulation to reality without losing or degradation of the policy of our agents. Thank you for your attention. You have questions?